Hello students, and welcome back. In our last class, we saw how graphs can give us a wonderful visual story of an object's motion. Today, we're going to take the next step. We'll learn how to move from just seeing the motion to actually calculating it with precision. And for this, we will be using the very powerful tools of mathematics, the equations of motion. So, here's our plan for today. First, we'll quickly touch upon why we need equations in the first place. Then, we'll get to the heart of our lesson, the three key equations of motion. After we understand them, we'll see how to apply them to solve problems. Then, we will explore a very interesting topic called uniform circular motion. And finally, we'll wrap it all up with a quick summary of everything we've learned.
All right, let's start with our first section. Why do we even need equations?
Now, if you remember from last time, graphs are fantastic. A distance time graph or a velocity time graph can tell us the whole story of a journey at a single glance, whether something is moving fast or slow or speeding up.
But think about this. What if you need to know the exact final velocity of a train after, say, 15 seconds, or the exact distance a cricket ball has traveled in the air? Drawing a perfectly accurate graph for every single question, well, that's just not practical, is it? We need a method that's faster, more direct, and more precise.
And that method is, of course, the equations of motion. But before we just write down the equations, we first need to learn their language. We have to understand the meaning of each symbol they use, like learning an alphabet.
First up, we have the letter U. This represents the initial velocity. It's simply the velocity of the body right at the beginning, the moment we start observing it.
Next, we have V. Now, if U is the starting point, V is the finishing point. It stands for the final velocity. This is the velocity the object has at the end of the time period we are interested in.
Then we have A. This is for acceleration. Now this is a very, very important point to remember. In these equations, we are always talking about uniform acceleration. This means the velocity is changing at a constant, steady rate, not in sudden bursts.
The symbol T is quite straightforward. It's used for time. It's the time interval during which the velocity changes from its initial value u to its final value v. And finally, the symbol S represents the distance, or the displacement, of the object during that specific time t.
Okay, now that we know the symbols, let's look at the first equation of motion. It is v equals u plus at. Let's try to understand what it's telling us. It simply says that your final velocity, v, is equal to whatever velocity you started with, u, plus the total change in velocity. And that change is just the acceleration, a, multiplied by the time t. Simple, isn't it?
Now for our second equation. S equals ut plus half at squared. This one helps us calculate the distance. Think of it in two parts to make it easier. The total distance s is the sum of two things. The first part, ut, is the distance the object would travel if it just kept moving at its starting speed u. But it's accelerating, so it covers some extra distance. And that extra distance is the second part, half at squared.
And here is our third equation. 2as equals v squared minus u squared. This equation gives us a direct relationship between acceleration, distance, and the velocities. And here's a helpful tip for your exams. This equation is your best friend when a problem does not give you the value for time t. It helps you find the answer directly.
So it's one thing to see the equations, but the real learning begins when we actually use them. So let's try to apply them now. We are going to solve a problem from your book together, and we'll take it one step at a time.
Before we solve, it's very important to have a clear method. This four-step approach will help you solve any numerical on motion correctly. Step 1. Read the question very carefully and write down all the values that are given. Step 2. Clearly identify what quantity you are being asked to find. Step 3. Look at your three equations and select the correct one that connects what you know with what you need to find. And finally, Step 4. Put the values into the equation and solve carefully. Let's solve example 7.6. The question says, a car accelerates from 18 kilometers per hour to 36 kilometers per hour in 5 seconds. Find the acceleration and the distance covered. Okay, step 1. List what is given. Initial velocity u is 18 kilometers per hour. Final velocity v is 36 kilometers per hour. And time t is 5 seconds. Now, please pay close attention here. This is a very common place for mistakes. The velocities are in kilometers per hour, but the time is in seconds. We must convert everything to standard SI units, which is meters per second. To convert kilometers per hour to meters per second, we multiply by 1,000 and divide by 3,600. So u becomes 5 meters per second, and v becomes 10 meters per second. Now our units are consistent. To find acceleration a, we use the first equation. A equals v minus u divided by t. Putting the values in, we get a equals 10 minus 5 divided by 5, which gives us 1 meter per second squared. Now, to find distance, s, we can use the second equation. S equals ut plus 1/2 at squared. Substituting our values, we get s equals 5 multiplied by 5 plus half multiplied by 1 multiplied by 5 squared. This simplifies to 25 plus 12.5, which equals 37.5 meters. You see, by following the steps, the problem becomes quite simple to solve.
So far, we have discussed motion in a straight line. But motion isn't always straight, is it? So now, let's turn our attention to a very interesting type of motion. Let's explore uniform circular motion. Let me start by asking you a question to think about. Imagine a car is moving with a constant speed. Its speedometer is not changing at all. Can this car still be accelerating? It may sound strange, but let's investigate. Please look at the image on this slide. An athlete is running on a rectangular track. He has to change his direction sharply at the 4 corners. Now, if the track was hexagonal, he would have to change direction 6 times. On an octagonal track, 8 times. You can see the pattern, can't you? As we increase the number of sides of the track, the path becomes more and more like a circle. And on a perfectly circular path, the athlete has to change his direction at every single moment.
And this brings us to the most important point. We must remember the definition of velocity. Velocity is not just speed. Velocity is speed times direction. So even if the stone in this picture is moving with a constant speed, because its direction is changing continuously, its velocity is also changing continuously. And what is acceleration? Acceleration is the rate of change of velocity. So if velocity is changing, there must be acceleration. This is why any object in uniform circular motion is always accelerating.
If we need to calculate the speed of an object moving in a circle, we can use a simple formula. The speed v is equal to 2 pi r divided by t. Here, 2 pi r is just the circumference of the circle, which is the total distance covered in one round. And t is the time taken to complete that one round. So you see, it is simply distance upon time.
We have covered some very important concepts today. Before we end our class, let us quickly summarize the main points we have learned so they are fresh in our minds.
So what are the key takeaways from today's lesson? First, the 3 equations of motion allow us to calculate motion with accuracy. They are v equals u plus at, s equals ut plus half at squared, and 2as equals v squared minus u squared. Second, we learned about uniform circular motion. We understood that it is an example of accelerated motion. And why is it accelerated? Because even when the speed is constant, the direction of motion is always changing, which means the velocity is always changing. Well done today. You have all done a great job of understanding these concepts. I would suggest you practice solving a few numerical problems using these equations. In our next session, we will conduct a full revision of this entire chapter on motion. Thank you.